No, that makes sense with the beginning. Right, if you keep doing it and you keep, the more you learn.
Wasn't that bad from the start? And then you're like, wait, I did that part wrong. Yeah, it's all this wrong. No, I'm like, yeah, I was wondering if I was reading that. Yeah, that's fun. That's good. That's it. Yeah, yeah. It's gonna be there, right? But is there any answer that's not?
All right, let's start because I don't see anybody else showing up. Don't forget we're talking about regression, right? So when I say Bayesian model selection, the examples I'm going to give you will be in the context of regression, but literally the subject area is very general. So the same ideas would be applied if you have a classification problem, some type of unsupervised learning. So I wanted to insert these slides on because the algebra is the same for any problem, okay? So we did the basics of regression. I heard that some of you did not look like regression, okay? But we're coming back tomorrow to continue on regression, okay? And actually tomorrow the lecture is going to have very few things new. So there will be some examples. And then I'm going to repeat the regression details where the noise in the likelihood is unknown, which is more practical. So the equations will look way more complicated, but somehow we're going to put some prior on the noise and we will compute a posterior for the noise as well. Okay. So today what I wanted to do is discuss a little bit about Bayesian model selection. The subject is a little bit different, okay, from usual topics, but is essential. I mean, you have to do this type of calculations that we will discuss today in most type of model development. Okay, so one of the things we discussed is that maximum likelihood estimation is not good for you because you overfit. Okay, so now if you overfit, right, means you have to somehow do something to control the model complexity. And the way we discussed this in a non-Bayesian way was to control the regularization parameter. You remember when we optimized the square error and then we put some penalty with a lambda term? That lambda controls basically how complex the model is, okay? And another way to do this is, especially in the non-Bayesian world, is to effectively do what is called cross-validation. So effectively, to figure out what is the best complexity of the model that you want to have, you split the data, let's say in this case, in 4 parts. You train it on 3 parts, and then you do predictions on the last. And you iterate on this data set being different partitions of your whole data set. And then somehow you average the performance when you do this cross-validation process. So what you see here is called leave one out cross-validation, okay? And literally, if you look on every non-Bayesian paper that does statistics, they do this sort of thing, and they tell you the cross-validation error is equal to that. You will see it somewhere written, okay? Now this, some Bayesian people do this as well, but it's usually not advisable because in essence saying, I am going to use this part of the data for training and this for testing, somebody would say, why waste that part? I mean, if you only have, let's say, 5 data points, why should you use 4 if you have 5? All right? So the Bayesian way is you use what you have, all right? But still, some Bayesian people do this as well. All right. So we will discuss today different sort of criteria for controlling the complexity of the model. And one of these criteria that I think it was in your homework set or some version of it, it was effectively you control, you maximize the log likelihood the way you get an MLE estimate, but there is a penalization that controls the complexity of the model. And in this case, let's say for regression, m was the order of the polynomial that you use for regression. So that way you say maximize the likelihood but don't allow for polynomials of very high order. Okay? So what we will do is formally we will actually derive sort of a method that will give us different forms of criteria that somehow we can use to control complexity, and we will do this in a fully Bayesian way. Okay, we will do this in a fully Bayesian way. All right, so in a fully Bayesian way, literally what you need to do at the end of the day, if you have many models and you want to compare them, you need to compute the posterior over models. And that's a weird concept, right? We have said the posterior of parameters, but here M is a model, so you can think M M equal to 1 may be a regression problem, a model with linear basis functions. M equal 2 with quadratic, M equal to 3 with cubic, right? So what the idea here is, each model is trying to explain the data. How about if you select a model, all right, that has the maximum posterior over the data set? Okay? Now you notice in the equation here, this is basically Bayes' rule written in terms of data. This calligraphic D is my data. You don't see any parameters, all right? So to do this type of calculations, obviously you will require to integrate over the parameters of each model. All right, so, and I will give you the formulas. They are not, so they will be sort of marginal likelihoods. Okay, obviously you're going to need some prior over models, and because usually we don't really have good idea of what model may be better than another, you can think of this being a uniform distribution over models. So really maximizing the posterior over models will turn out to be the same as maximizing the marginal likelihood of each model, which is the evidence of each model. Okay? So again, if P of M is constant, it's equal to 1, all right? So all models have the same probabilities. Effectively, this is proportional to the marginal likelihood. Okay, so what is this marginal likelihood for each model? Because we can only calculate the likelihood of the data given the parameters, so effectively you can see this calculation written as that. So this is the prior for model M, this is the likelihood for model M if you knew the parameters, and then you integrate the parameters out. Okay? If you get confused, this is the same equation we have seen for the normalization factor in Bayes' rule, right? The only difference is we didn't explicitly indicate M because there was only one model, so now we say for model M, okay? So for model M, this is the likelihood, the prior, and then all the parameters are integrated out. Now, keep in mind, and I may give you an example in the lecture today, if you compare models, these parameters theta don't have to be the same in all models. So one model may have only one parameter, another model 50 parameters. Okay? And in the context, let's say, of physical or engineering applications, one model can be a discrete model, another model can be a continuous model, can be anything you want to, right? This is just a distribution, it's how basically each model explains the data. And exactly what the origin of the model is all about, it's not important. Okay, now what people will do, right, is will actually go and fix the parameters. So rather than doing this complicated integral, okay, what they will do is they will say, you know what, how about if I fix the parameters to a point estimate? And a good point estimate would be, let's say, the maximum likelihood estimate. So you can see from here, if the parameters are fixed to maximum likelihood estimate, this becomes a delta function around the MLE estimate. And effectively, this marginal likelihood is basically the likelihood calculated at the MLE value of the parameters. You see that? So basically what I'm saying, if you don't allow the parameters to vary, right? And you say, I'm going to fix my parameters to be my MLE estimate, then this integral, this becomes a delta function, and then this integral is effectively the likelihood computed at the MLE estimate, which is what I indicate here. All right? Now, this doesn't work, and it doesn't work because if you try to maximize, let's say if you try to compare models with different parameters, maximizing this, where the parameters are fixed to a point estimate, guess what? This likelihood will get bigger and bigger the more and the more parameters you use. The higher the complexity, the better. You never stop. All right? So the idea of fixing the parameters, basically, the more complex model, the better. Okay? And for any model you give me, I can give you something better by making it more complex. So this is not going to work. And the ingredient here that where all the issues come is because the parameters are fixed. Okay? So what do you need to do to get rid of this issue is not fix the parameters, but integrate them out. Average over the parameters. Okay? So you don't fix the parameters, but you integrate them out according to this formula. So that way, you know what? A model can have millions of parameters, and you compare it with another model of 10 parameters. It doesn't mean that the model with millions of parameters is better, because at the end of the day, when you look at this, parameters have been integrated out. This is extremely important, okay? This is sort of a basic ingredient of this Bayesian model selection, that somehow you need to integrate the parameters out. If you don't do that, effectively the more complex model, the higher the evidence, and that will not be useful. All right. This actually slide puts some analog. I am not going to discuss it. You know, some intuition basically why this, what the statements I make sense, using ideas from cross-validation, so you can read it or ask me a question. Okay, so actually let me go directly on this slide. So let's say we collect data X. We have multiple models, and I call this, it's model M1, M2, etc. So this is model MI. And what you see here is the posterior of the parameters for model I. Nothing fancy, right? So this is the likelihood of my observations for model, knowing the parameters for model I. This is the prior of the parameters for model I, and this is the marginal likelihood. Okay? And you remember what we're really interested is to compute the posterior over model. So given the parameters, we want to know what is the posterior of model I. So actually, you know what? If you think of Bayes' rule for this, really what this is the marginal likelihood of model MI times the prior of model MI divided by P of X. So this is Bayes' rule. This is Bayes' rule over models. And now you appreciate that the normalization factor that we have seen for writing the posterior over parameters, right? It is extremely important for model selection. Because to compute the posterior over models, you need to know the marginal likelihood for each model. Okay? So again, this is what we have seen up to now in the course, right? The posterior over parameters. And this is the normalization factor that we get. So it's basically the marginal likelihood of the data for model MI. And now what I'm using is I'm using this to write, again, Bayes' rule to compute the posterior of model MI. So basically, what's the posterior, right? Is, what's the probability of MI given X? Right, so considering that I have collected data, what is the posterior over model MI? And it's nothing else but the likelihood, how model MI explains my data X, times the prior of model MI, divided by this marginal of X that does not include any model. So actually you can envision that P of X, it's actually the numerator where you sum over all models. And maybe even that may have some purpose. Okay, but let's leave it out for now. Okay, so this is the posterior over models. All right, so let's write a few things. So this is this likelihood basically for model MI, And will you agree with me that, look at this equation, okay? Here there's no theta, there are no parameters. And I already gave you the formula. How do we compute this? It's effectively you introduce the likelihood given the parameters times the priors of the parameters for model MI, and then you average over all parameters, okay? So effectively, again, the posterior over models is proportional to this marginal likelihood that you see here. And so this is the best you can do in a Bayesian setting. In a Bayesian setting, there's no, it is not as easy to say this model is better than every model, but you can say maybe model M1 is better than model M2. And how do you do this? You take the ratio of this two posteriors over two models. So let's say we have model M1 and M2. If you take the ratio of this, the P of X will cancel out, and what you get is you get the likelihood, the marginal likelihood on the model M1 divided by the marginal likelihood on the model M2 times this ratio of the priors of model M1 and M2. And I am writing these likelihoods explicitly, okay? So this ratio that you see here of the two integrals, it's what is called the ratio, this is the Bayes factor basically. Okay, this is a Bayesian way to compare two models. And you can see that this ratio of the posteriors is really this Bayes ratio if the priors are uniform. All right, so if they're uniform, you put them equal to 1, they cancel out. So effectively this posterior, the ratio of the two posteriors is the ratio of this marginal likelihoods defined by this Bayes factor. All right, so let me summarize because there is a lot on the slide, right? So we're trying to compare different models. Think of models here being, different orders of polynomials. Let's say when you do regression, you say, should I use a second order, a third order? So each of them I indicated here as M1, M2, etc. Now each model has its own likelihood, marginal likelihood. This is the marginal likelihood. Remember, to write the likelihood, you can only do it if you know what the parameters are in regression, right? So you have to introduce the parameters and then you integrate them out. So this is actually the denominator in the posterior of the parameters over each model, okay? So the ratio of the two posteriors of two models, M1 and M2, is this ratio of this, I don't know, it says here ratio of Bayes factors. So if you want to call this a Bayes factor, I call the whole thing the Bayes factor basically, okay, times the ratio of the two priors.
Why do you assume that the ratio, that the ratio of the prior, that there's not a difference in the priors?
You will see when I will do, who was asking the question? Yeah, so somehow with my microphone, my ear is, So we will see later on, right, that somehow if this comes in the picture, you can get any answers you want to, depending what priors you put. So you're completely lost, basically. So the best thing you can do is to say, all models are equal to start with, and let the data basically make the difference. Okay, so you will see in an example that I have, effectively, whatever you put in that ratio, you can get any answer you want for the posteriors. So you can.
It's always true for priors, right?
Yeah.
But there could be some prior knowledge.
If you have some prior knowledge, add it.
Okay.
Yes. So basically, literally, right? When you see the Bayes factor alone, means that they take this to be uniform and basically take them equal to 1. When you don't see them, means they are putting something on these priors. Okay. But eventually, at the end of the day, really, this is our objective. If we only use this, we do some assumptions on the priors. Okay. All right. So let's do a very simple example. This is a coin example. Let's say you have two models, all right? And one model says the coin is fair, okay? And I'm using a prior for the fair coin that is a beta distribution. As we have seen for the binomial, this is what you use. And actually, if you put the numbers, you will see why this looks, I am guessing this thing must be picked around 0.5, basically, all right? And then the second, it says M2 is unfair, so you put a prior that has parameters alpha and beta 0.5 and 0.5.
So let's say you collect now data, you flip the coin 5 times, you collect 2 heads and 3 tails, and so the biggest factors basically is is this ratio, okay? So the likelihood, you remember the likelihood is basically the binomial distribution, so I get 2 heads, theta squared, and 3 tails, 1 minus theta cubed, times, what is this? This is this prior. You remember the beta distribution is theta to alpha minus 1, 1 minus theta to beta minus 1. And this is the normalization factor from that prior. And similarly here, I have basically the same likelihood, okay? The only difference is the prior now is theta minus 0.5, 1 minus theta minus 0.5 divided by this normalization factor. So you get this ratio. And when you actually put everything together to compute the posterior, it comes the posterior of model M1 for this data set divided by the posterior of M2 is 2 times 58 times the ratio of the priors. Okay? And now, obviously, when you look at that data set, right, are you going to say that this is an unfair coin? Are you going to put more probability on model M2 as a prior? I suppose you don't suppose to have seen the data, but anyways, you can see here that somehow this ratio comes to be important, but if you don't account for that ratio, the fact that this is 2.58 points towards model M1 being the correct model, okay? But actually we will see that the statisticians have a scale that maybe 2.58 for this Bayes factor is not good enough to say M1 is best. And I'm going to show you what that scale is, okay? But obviously, number-wise, it looks that M1 has higher chances than model M2. All right, so this is the same example now, the same 2 models comparison, but the data is 5 heads. Obviously, you can look at the data, right, and say, you must be kidding, this is not a fair coin. You're not going to do this 5 times and get 5 heads. So if you compute for this, you put the correct likelihood now corresponding to 5 heads. Guess what? The probability of the posterior of M1 versus M2 comes to be 0.13. So now this points immediately that the model, the dominant model here that explains the data is M2 and the coin is unfair. Okay? All right? Okay. Now, again, in case I don't have time to finish the slides, right? It says here, this Bayes factor should be used with extreme caution when the priors that you use are non-informative. Okay, and as you said, if you really have information, put it in, because if you have non-informative priors or the limit of informative priors, you can actually get any results you want to. Okay, so sometimes reviewers will ask you to add the Bayes factors, but we will learn today a little bit better things to do in addition to the Bayes factors. All right. So this is an extremely important visualization of these issues of model complexity and model selection. So hopefully you can understand it. Okay, this picture you will see it in many books, in many papers, and it's like at the end of the day, nobody knows from where it came. If it was David Mackay or Zubin Garamani in this tutorial. But let me explain this picture. So what we do is, right, we're looking at different models, and we're trying to see what type of data sets these models can explain, and with what probability they can explain different data sets. So on the horizontal axis, imagine, because you need to imagine here, okay? Imagine different data sets of different complexity, basically. So in the regression problem, not like here there's a few data sets, but you have another data set and another points here and there, right? So I am looking at model M3, and you notice covers a lot of data sets, which means the model M3 can explain a lot of data. But if you can explain a lot of things, the probability you affiliate with each of these data sets has to be small. Why? Because if this is a probability and you sample over all possible data, then this has to be normalized to 1. So the fact that model M3 can explain lots of data, it needs to explain all of this data with low probability. Okay? So again, sort of I'm using a non-Bayesian explanation here because we're playing about different data sets, right? I mean, in a Bayesian setting, we only have one data set, but I want to bring this concept of this Bayesian Occam's ratio, okay, and how we compare models. So M3 explains a lot of models, but because of this normalization, it explains each model with very low probability. If you take now M2, it is of some intermediate complexity model. It explains less data sets, okay, with a higher probability. And if you go to model M1, it explains only very few data sets, right, with very high probability. So you can think of this being a model that is like a linear fitting to data, all right? You can only explain linear data. This is a polynomial of order 200. You can explain anything you want to, but everything with very little probability. And this is something in between. Now, in a Bayesian setting, you say, my data, my observations are D0. What is the best model? And the idea here is the best model is the model of intermediate complexity. All right? So in our case, basically, the best model that explains the data is model M2. Okay? So again, this picture looks at the probability each model assigns to different data sets. Okay? Don't forget this normalization here. Okay? And the idea here is we will assign the data to a model of some intermediate complexity that basically gives you, in this case, you can see basically we are selecting the model that best explains this data with the highest possible probability. And that model is model M2. Okay? So, all right. And this thing in action for our regression problem. So this is, I mentioned M1 is, straight line. Okay, M2, let's say it's a quadratic. Okay, that's an intermediate complexity. And M3 is something that overfits overall data sets. All right, so really what you need to do in this particular case, we select this intermediate model M2, okay, that maximizes the probability of the data. And if you remember, the probability of the data is the marginal likelihood that we're talking, right? The marginal likelihood, and so that's a model of intermediate complexity. I mean, the first time you see this picture, sort of, it's, I mean, even though it's easy to understand it from a practical point of view, right? But you have to extend yourself a little bit beyond the Bayesian setting to get the sense of what this means. And of course, when you try to actually do it in practice and produce a plot like this, all right, a plot like this for regression, let's say, then you really get a good appreciation. So the way we're going to do this is basically these posteriors over models will help us to guide us in reproducing something like that. All right. So again, actually, this is the regression problem with model selection and model comparison in action. So we are looking to fit polynomials of different orders. Let's say linear, quadratic, cubic, to 5 data points. So we have very few data points. And so we do the Bayesian regression scheme as before. These are the data points, the circles that you see here. This is the generating function of this data. We don't know that function, but this is actually the sort of the true solution. And here is linear fitting, straight line. These are the error bars. You remember in the predicted distribution, you have plus minus sigma. All right, so this is the error bars in your predictions. So this is when you use a linear model.
This is when you use a quadratic, so this is the mean predictive distribution. This is the mean of the predictive distribution, and this is now a polynomial of order third. And more importantly, what you see on this last picture is the posterior over models. So when you look at the posterior over models for a situation with 5 data points only, these 5 data points, which model is the best? Look at that. Don't look at the results. First look here, what this tells you, and then go back and look at the results. So which model is the best based on these posteriors? The straight line, all right? It's model 1, okay? And, you know, you can sort of, you know, I mean, you can visually see it actually, all right? But in this case, with 5 data points, really the best model is model 1, okay? Now, keep in mind that don't look at the mean prediction and say, you know, but the mean prediction looks better for this or that, because you also, what is accounted in this is, right, all possible values of the parameters and the uncertainty induced here. Look at this uncertainty. So implicitly, in doing these calculations, these type of things are integrated in the model, okay? So this is the calculation for 5 data points. And now let's repeat this for 30 data points. Now, which model is the best? It's 2, okay? And again, this is a nice principal way to, you know, to do model selection, okay? This is the best way to compute these posterior over models, okay? And in this particular implementation, and actually the program I give it to you here, these priors over models are taken, they follow a Gaussian distribution. So there is a prior over models that's being used as well. You may think sort of that these calculations would be 50 pages of programming, and you know, if you click this PMTK library, you will see the whole calculation of doing this for regression is literally 5 lines. Why? Because this calculation of even the posterior has an analytic expression. You know everything. Given the data, that's the expression, and calculates it in 1 line, and you're done. And I'm going to teach you actually today how you do these calculations. Okay? So I'm going to throw some algebra to see for different models how these sort of calculations are done. All right. So basically, as I said, I'm going to show you. It says here, when comparing models, you need to know how to compute the marginal likelihood. So basically, the denominator in Bayes' rule, when we did the posterior parameters, it's extremely important for doing model selection, okay? Because this is what you get in the denominator. So when you write this equation, right, the denominator is this. And later when we will start doing sampling methods, you don't really need to know this. You only need to know the posterior in up to a factor, okay? But to do model selection, you need to know this marginal likelihood, and that calculation is very complicated. And by the way, that calculation has a lot of physics involved with it, and so everything important in life, right, comes from you know, from free energies, and the free energies are very much affiliated with this marginal likelihood. Okay, so model selection, this is what we need to compute. So let me give you the calculation. I know I went through this rapidly once upon a time. It looks like last year, but it was a few lectures ago, and maybe at that time it wasn't making any sense, but let's try to redo the calculation thinking of regression, for example, okay? So let's look at our Bayes' rule. So we're looking at a model, right? And we want to compute the marginal likelihood. We want to compute P of D, okay? So what I have here is the posterior of the parameters is the likelihood times the prior divided by P of D, okay? Now, think that every distribution, all right, these are, you know, this is a distribution in theta and theta.
this is a function of theta. Think that somehow, when you plug in all of these distributions, the terms that involve theta will cancel on the left and the right hand side, and the only thing you will be left will be the normalization constants on the left and the right hand side. We agree? So for example, if this involved, let's say, theta squared divided by some number, when you multiply those two, there will be another theta squared, the two theta squares will cancel out. So what I do here is the following. I am writing all of the distributions that you see as some function of theta divided by the normalization factor. And all of these functions of theta will cancel out on the left and the right hand side. So what I do here is I write the posterior as some function of theta divided by the normalization factor, and I denote this Zn to remind me that I have n data points, right? So it's the normalization factor of the posterior when I collected n data. Similarly, I have here the prior, which is some function of theta, that's the normalizing part of the prior, divided by the normalization factor Z0. And then what I have is the likelihood, okay, which is a function of theta directly, divided by some normalization factor of ZL. So this is not 1, it's the normalization factor of the likelihood. And then I have the marginal likelihood there, P of D, that involves no theta. So when you cancel these functions of theta, what you get is that the marginal likelihood is this an amazing result. It is the ratio of the normalization factor of the posterior divided by the normalization factor of the prior times the normalization factor of the likelihood. So if you want to do a model comparison, what actually you need to do in your particular problem, and it doesn't matter if it's a regression problem, classification problem, anything, you need to actually compute these normalization factors for the posterior, the likelihood, and the prior, and P of D is directly the ratio of those. And if it happens that these distributions are in the exponential family, right, we already know what is normalization factors. They're in the book. So if it's a Gaussian, if it's a normal inverse wizard distribution, you know it's in the books. You go to Wikipedia, you copy, and immediately you have the model evidence, basically. So let me do a very simple example so that we can see how this thing works, right? So let's consider that we have a likelihood that's binomial. So this is like a coin flipping, but we flip the coin n times, and we count how many times we get heads and tails, okay? And if you remember the prior, it's a beta distribution. That's a conjugate prior, okay? So theta is the probability of getting heads. So I am writing the posterior equal the prior times the likelihood divided by P of D. So now let's look at the prior. Do you agree with me? The prior, if it's a beta distribution, is theta to alpha minus 1, 1 minus theta to beta minus 1, divided by the beta function to normalize it. This is now the binomial distribution. I have n1 heads and 0 tails, is the factorial of getting n1 heads out of n experiments times this. And then the posterior, it will be a conjugate, it will be a beta distribution. And what the beta distribution will be it will be a beta distribution with parameters a prime to be a plus n1. You can see if you multiply them and add them there, and b plus n0. So all the terms that involve theta here and theta there will cancel with the theta terms on the left-hand side. So what you are left is that for this case, the marginal likelihood is this factorial of n taken with n1, times the ratio of this beta function divided by this beta function that normalizes the prior. Okay? So basically with this trivial calculation, repeating the formula from before, I mean, we could have literally just look at the books what the normalization factors for the binomial and the beta distribution are and just plug them in, and that's the answer. Okay? You can do this, extend this further if you have a likelihood that is a multi-nully model. So you remember that's in one of, you have k-states with its own probability, and the prior is a Dirichlet prior, and then the posterior comes to be a Dirichlet posterior. So taking the ratio of these normalization factors, this is what the marginal likelihood looks like. And it looks very complicated, but actually if you look in the literature, they tell you how to take derivatives and find, the maximizer, if you like, of this function in terms of these parameters, because this is extremely important when you play with these distributions. You need to know how to do these derivatives. So let me, I'm going to do a real example now, okay? Do you remember when we did the Gaussian with both the mean and the variance being unknown? What is the conjugate prior? So when both the mean and the variance were unknown. And we did this for scalar, univariate and multivariate variables. So what was, for a multivariate normal, you remember it was normal inverse wizard distribution or normal inverse gamma. So effectively what you had is the mean was following a normal distribution given sigma square, and sigma square was following an inverse gamma distribution. So effectively, this is how this normal inverse wizard distribution looks in for the multivariate case. You can just look at Wikipedia, that's what I do, all right? And you can actually see explicitly the terms that involve mu and sigma, etc. And then there is a normalization factor that involves all of these nice goodies here, okay? It involves this multivariate gamma function, the determinant of the matrix S0 that comes on the inverse wizard. So this is the normalization constant. People have done that for you. So what do you need to do to compute the marginal likelihood? Take the normalization factor of the posterior, and remember the posterior is also normal inverse wizard because they are conjugate. Okay, so this will actually follow this, but instead of using parameters nu0 and s0, you're going to use the parameter nu subscript n and s subscript n, because those will be the parameters from the posterior. This is z0 from the prior, and then you have ZL being the normalization factor from the Gaussian. Do you recognize actually that this is the normalization factor from the Gaussian? 1 over 2 pi to the power n times d over 2. Think about it. Remember I have n data points, right? And to get the likelihood, I multiply all of these Gaussians. Every time you multiply, what factor do you get? 1 over 2 pi to the power d over 2. Because the Gaussian is d-dimensional. Okay? And times n, because you multiply this times n for n data points. And what happens to all the terms of the Gaussian? They have disappeared, because you remember when I used Bayes' rule, the functions of mu and sigma on the left and the right side cancel, and the only thing you're left is the normalization factors. Now you may say, oh, you know what, this is not important, n times d. If you miss this term, you are ruined. You know why you are ruined? Because this term involves n, the number of data points, but also involves the model complexity, which is d. So if you don't put that term, somehow your results will be completely wrong. So you have to sort of do this type of calculations with care. So when you do this, for this multivariate normal, it comes that the marginal likelihood is what you see here. That's it. Okay? So to do this type of plots, right, that I was showing you before, if you're, the regression thing, everything is a Gaussian, right? The prior is a Gaussian, and we even took the noise constant, but somehow even if you take the noise to be unknown, effectively the marginal likelihood that you need to compute the posterior of the models, you can copy this formula, you put in your computer program, and it just calculates it in one line. All right? So your effort, it is not to program this, your effort is to be sure that this calculation is correct. So it's not a matter of programming, because to program it online, it's a matter actually of understanding this calculation that involves the marginal likelihood. All right. Now I want to introduce, so we have to bring up these ideas to discuss various Bayesian criteria, if you like, for model selection beyond using Bayes factors. And before I do anything, I want to introduce what you guys have to do in the homework as well, which is called the Laplace approximation. And this is an approximation to the posterior over parameters, and it is fundamental to every high-dimensional problem. So when life gets complicated and you cannot handle the posterior because it's too complicated for you, you make it to fit to a Gaussian. And where is that Gaussian? It's fitted around the mode of the posterior. So the posterior, whatever it is, you say, I'm going to approximate it with a Gaussian. And that Gaussian will have a mean, the map estimate of the posterior, and it will have a precision, if you like, which is minus the second derivative of the log of the posterior. Okay? If you want sort of a slightly different mathematical derivation of this, how about if you think the following? Take the log of the posterior and do a Taylor series expansion in theta, keep only the up to second order terms, and approximate it around the theta map estimate. Then when you go from the log back to the actual posterior, then you get this approximation. And this is what is called a Laplace approximation. Simply what it is go to the mode of the distribution and fit a Gaussian with this basically precision. Okay? And you do this around the map estimate. That is called the Laplace approximation. It looks, a very crude approximation, but if you have a lot of data, the idea here is these posteriors are getting sharper and sharper around the mode. So the approximation of them as a Gaussian is not a bad one if you have a lot of data. So rather than trying to integrate over, let's say, this posterior that you can only sample from, what you can do is you can approximate it as a Gaussian, and then maybe you can do the integration over the parameter space analytically. Okay? So it's a crude approximation, but people are using it in research all the time. Okay? It is. You just need to know the limitations. So if you have something that is bimodal and you try to fit in actually a Gaussian distribution, then obviously that's wrong. Okay, it will not work. All right. So let me then start talking about how this Laplace approximation can help us actually to get this model evidence in sort of. How we can simplify the calculation of the model evidence. So the model evidence, you remember, so we are looking at model M. So you can actually, visually, you can get rid of this MM completely from all of these equations. So what I have is the marginal likelihood is really the likelihood, given the parameters, times the prior, and then divided by the posterior. Bayes' rule goes on the reverse, right? The posterior is the likelihood times the prior divided by the marginal likelihood. So I'm writing here that the marginal likelihood is the likelihood times the prior divided by the posterior. All right, so let's start taking logs. To do model selection, really we need to compute this. So the log of this is the log of this plus the log of the prior that you see here, all right? And then, where are all these terms coming? So I took the log of this and the log of that minus the log of this. Is that equal to that? This is the log of the posterior of the parameter. So what have I done there? What have I done there? I used the Laplace approximation. Because, right, the idea here is that the posterior of the parameters it's a Gaussian, approximately centered around the map estimate, and that's exactly what I have here. Okay, so I am taking basically here that I have d parameters, okay, and so if I approximate this with a Gaussian around theta map, okay, this is what I get. And what I do is now, I calculate this marginal likelihood around theta map. So I'm approximating, basically I'm putting the parameter theta everywhere to be the map estimate. And if you do that, this quadratic term disappears, and the approximation that you get for the marginal likelihood for each model is the log of the likelihood of the data plus the log of the prior plus d over 2 times log of 2 pi minus 1/2 log of the determinant of A. And what is A? Is minus the second derivative of the log of the posterior around the map estimate. Now you may say, thank you very much. This is very complex, but well, you know what? It is very complex, but I will simplify it for you, and you will see how all the Bayesian criteria for model selection are coming. Okay, so this is obviously not a bad term. This is the likelihood given the parameters around the map estimate. This is the prior. Okay, D is the dimensionality of the problem, and here is log of a determinant that has to do with the second derivative of the posterior, of the log posterior. All right. So we're going to take to define some Bayesian criteria for model complexity. I am going to take the assumption that n goes to infinity, that I have lots of data. Okay. So this is the equation that we had before, and now I am going to try to simplify when I have lots of data. Remember that this A, it was coming by second derivatives of the log of the posterior, all right? And if you think that the posterior is really the likelihood times the prior, as n grows, this matrix A grows also as n times some constant matrix. I mean, the more data you get, right, you anticipate sort of, we're really interested on asymptotic expressions here. But if n grows, A grows like n times some fixed matrix A0, and then that way when you take the log of A, of the determinant of A, when n goes to infinity, remember this determinant, so you're going to get log of n to the power d times the determinant of A0. So you get d log of n plus this constant term. So as n goes to infinity, you get d log of n. So as n goes to infinity, this is really constant. The likelihood increases with n, so you have to keep the term. And then what you have from here is minus d over 2 log of n. And this is basically what is called the Bayesian information criterion. Right? This is an approximation to the marginal likelihood that you will see in literature. Everybody is using to say something about the selection of the model. So to select models, we need to know the marginal likelihood for each model, and the approximation we use is compute the likelihood for parameters fixed at the map estimate. That you can do, right? Likelihood is your computer code, but you fix the parameters at the map estimate, so you need to compute the map estimate, and then you have minus d over 2 log of n, okay? So you notice you penalize models of high complexity because d is how many parameters you have. So the more parameters, the more complex the model. So if you try to maximize this, the maximization will say, well, but you cannot have d very high, right? Because there's a minus sign there. So maximize the likelihood, but keep the model as simple as possible, all right? And this is, again, what's called the Bayesian information criterion. Is this what you did in your homework? Or it was some version of this, and I think instead of having the map estimate there, most probably you had the MLE estimate. And most probably, instead of having log of n, d over 2 log of n, you had something else, possibly m or something, some other approximation that controls the complexity. But when you do it in a Bayesian way, this is what you get. And this limit, this approximation is correct when n goes to infinity. All right, so you may say, it's too complicated for me. I'm going to drop the class when you give the third homework. So let's see what the third homework could have been. And it may be, I don't know. How about if you do regression, linear regression, the way we saw on, I don't even know what day is today. It's Thursday, so on Tuesday, okay? So we saw this on Tuesday, and I remind you what we did, on Tuesday we defined, in passing I gave you what the MLE estimate of the parameters is, which is a least squares estimate, all right? And this is actually the MLE estimate for the noise, okay? And the log marginal likelihood, if you compute it around, not the map estimate that I have here, but the MLE estimate, takes this nice form. And you may say, wait a second, from where is this coming? Well, you remember the likelihood given the parameters, they're all Gaussian, so if you multiply and you take the logs, you get, this is from the denominator, right? You get minus n over 2 log of 2 pi sigma squared, and then in the numerator you get this from the exponential divided by that. And if you use the MLE estimate for all the parameters, you remember the MLE estimate for sigma squared is this divided by n. So really what you get is here n over 2. So for this Bayesian information criterion for the regression problem takes this extremely simple form. Minus n over 2 log of 2 pi sigma squared, this is the MLE, minus n over 2 minus d over 2 log of n. So again, to put this in the computer, it's one line, but you need to know what you put in. Okay? And so I strongly suggest, right, that you try to appreciate that these calculations, they are not sort of magic. You take the Gaussians, you multiply them together, you take the log, this is what you get. Now you fix the parameters rather than fixing them at the map estimate that I had here, all right? Because that will take a little bit more effort. You fix it at the MLE, and the MLE estimates for the Gaussian, if we put a Gaussian prior on W with a Gaussian likelihood, everything is a Gaussian. The MLE estimate is what you see here, and the big criterion looks like that. If you put this on the web, right, and you say Bayesian information criterion, you will see, several millions of links to papers, because the idea here is this is what will define for you the appropriate model complexity that explains the data that you have at hand. All right, this we don't need this a modification. There are various different versions. So this is the Hierarchical information criterion. It looks a little bit different from what we derive on a Bayesian way. So on a Bayesian way, remember where was it? The complexity term here is minus d over 2 log of n. Okay, so if you use this, actually the complexity, it only accounts the degrees of freedom of theta. Okay, and it is computed around the MLE estimate. Okay, so this is a non-Bayesian way of doing this. And notice something very important. There's no n here. All right, so there's no n here, which means this model really picks more complex models than the Bayesian criterion. Because the Bayesian criterion penalizes you more because there's a factor there of n. All right, so if you use this AIC criterion, basically has the tendency to pick up more complex models than the fully Bayesian way. Bottom line, right, whatever criteria you use is going to be some form of the log likelihood, all right, some form of the log likelihood, some approximation, minus some term that penalizes high complexity models. So there is a very principled way to derive this in a Bayesian setting, which is this way, this is what you get in a Bayesian way. And there are hundreds of different approximations that, some of them non-Bayesian, that look similar, but they're a little bit different. They are approximations, very rough approximations to this log marginal likelihood, if you like. All right. Okay. I know I'm going to do this. Let me see what the next slide is, and if I have to bother about this. Yeah. So let me. I'm going to do this. I think next week, right? But let me, since we have discussed about these hierarchical Bayes models, let me bring this thing back. So we talked about marginal likelihood and maximizing the marginal likelihood. And you remember the marginal likelihood is that, in the regression problem, if W are the regression coefficients, to get the marginal likelihood was an integral of the likelihood times the prior on W with W integrated out. But how about if W has its own prior with its own hyperparameters? And I remind you, in our simple regression problem that we will revisit tomorrow again, we put a prior on W that was a Gaussian, but we took the precision of that Gaussian as an unknown parameter. So somebody will say, how do I calculate then this integral, because now I have to integrate on W and on alpha? Well, you have to do empirical Bayes. And what is empirical Bayes? Who will remind me? So what do we do with this hyperpriors in hierarchical modeling? So we have W now with a prior that depends on alpha. So do we integrate on alpha, or we can do something simpler? What was the idea? Point estimate. So what exactly we will use is, we will actually fix alpha and approximate the marginal likelihood like this. And then you say, and to what value do I fix alpha? You fix alpha at the value that maximizes this evidence, all right, where the evidence is written as a function of alpha and W is integrated out. Okay? So basically this evidence is literally what we had before with W integrated out, but we leave, because this prior depends on alpha, we consider the whole integral as a function of alpha, and we compute the argument alpha that maximizes this marginal likelihood, and then for this alpha, we plug it in on this marginal likelihood, all right, and we do the business. And I know it gets confusion here, because you look at this equation, right? This is a marginal likelihood, okay, where alpha is fixed, okay? And this is another marginal likelihood, okay, where we integrate on W, but before we fix the alpha, we maximize this with respect to alpha. So this is the method that's called basically empirical Bayes formulation, okay? It's standard in hierarchical Bayesian models. What you need to remember, if you have hyperparameters, usually they are of lower dimensions on W, which means there is no overfitting there, having them. So you do a point estimate, and a good way to do a point estimate, not to guess it, but to maximize the evidence, okay? And the evidence is basically the marginal likelihood expressed as a function of these hyperparameters. We will actually do this explicitly, I think next week, when I will revisit the regression problem, and I'm going to actually do some sort of magic with this prior on W to allow to do what is called relevance determination. So basically, if you have W, a big vector with lots of parameters, I will use a prior that somehow will allow me automatically to figure out which W's do I really need. So if you have an input, and each input, you have an input vector x1, x2 to x50, do you actually need all these input values to predict, let's say, the response of the system? All right? And so if you use some smart prior, it can automatically say, you know what, x7 is unimportant, the height of the trees, who cares, the depth of the sea, who cares, and all of these things would be disappearing out of the formulation. And this is what is called relevance determination, and really has to do with selecting some smart priors that will simplify this calculation. So we will do this next week. I promise you that I will give you a table. Maybe I should have put this earlier, but since obviously we're finishing with Bayes factors, if you're comparing two models and you want to know, so you're comparing model 1 and model 0, and you want to know what model the evidence points to as being the correct model, basically these are the correct numbers that in the literature they tell you. For example, if this Bayes factor is less than 100, you say you have a strong, very strong evidence for M0. If it is less than 110, you have a strong evidence, not very strong, moderate evidence, weak evidence, etc. Okay, so you can consult this table for. Basically, the idea here is don't get excited when you use Bayes factors and select one model versus the other until unless the evidence is overwhelming. If the evidence is so, you say, sorry, so, I cannot use any of this. It doesn't make sense. All right. I only have 9 minutes, so the rest actually, they're not very important topics, right? So let me see what I'm going to tell you from all of this. We already have done this, so you can actually, maybe I should do this example, okay? So let's do the following example. This is, we're trying to compare two models, all right? And we're going to calculate the posterior of the models and Bayes factors and see, again, which model is the best. A model M0 is going to be a fair coin, so the probability of heads and tails is equal to 0.5. And then we have a biased coin, where theta is a uniform random variable from 0 to 1. So it can take any value from 0 to 1, right? So it's a biased coin, and so this is hypothesis M1, this is hypothesis M0. So to compute the Bayes factors, you remember we have to compute the marginal likelihoods. You agree with me if I have n points, that the marginal likelihood under the fair coin is this? Every time it's 1/2 the probability, so 1/2 the power n. If you have the unfair coin, the marginal likelihood, this is our formula, and the prior here, it's uniform in 0 to 1, all right? So when you put this, this integration in theta for this distribution, basically, I already derived this earlier. You get the ratio basically of this of the normalizing factor for the posterior divided by the normalizing factor of the prior. So effectively, if you plot those two things, they look like that. So let's compare. This is the Bayes factor of model 1 versus model 0. And what you see on the horizontal axis is the case of 0 heads, 1 head, 2 heads, 3 heads, 4 heads, and 5 heads. So look at this plot, right? And tell me, let me see on what data do we have. We have n equal to 5, and we observe 2 or 3 heads. So what you see here is, for 5 data, and we observe 2 or 3 heads. Do you think, before you do any calculations, this is a fair coin? 2 or 3 heads out of 5? Reasonable, okay? So let's see when you do this Bayes factor of model 1 versus model 0. It basically, it says if you collect 0 heads, the Bayes factor is very high, so model 1 dominates, and model 1 is the unfair model, okay, the biased coin. If you have only 1 head, it says, you know what, okay, these are about the same, all right, but certainly you're not going to be saying that this is a fair model. And then look what happens. When you have 2 heads or 3 heads, which model dominates? This is below 1, so it is the fair coin. And then again, at the extremes, when you have 5 heads, basically the Bayes factor goes up. Okay? If you do this with Bayes factors, or if you do this with these marginal likelihoods, they're actually, these plots are, they are sort of the same plots as the marginal likelihood with different scales. It just comes that in this case, basically both approaches give you the same story. And I think this, yeah, it's the same thing. Okay, so we don't really know. We don't want to worry about this. Okay. Let me see. Okay, so there's nothing here. It's a repetition of the same formulas that we have seen. So let me, let me take things to a little bit to an extreme, right? So let's say we have we have two models, and one model says the parameters are in the region theta 0, okay, and the other model says the parameters are in the region theta 1. And then you assign a prior for this case that's pi 0, and a prior for this that's pi 1. Okay? So, so basically you can think of this model being model 0 and this being model 1. Okay? What I plot here is the mixture prior of the parameters theta. So if you have two models that explain the parameters, right, you can either be a model 0 with this prior or model 1 without prior. And so this is the mixed prior, okay? It's an elegant way for writing this for the parameters, the mixed prior. And what I do is, to go to some extreme scenario, I am considering that model 0, the parameter is fixed, there's only one value. All right, so basically on model 0, it says the parameter is fixed, and that's what this indicates here, that the prior is basically a delta function. Is the indicator function. But model 1 has a prior that is pi 1. And you notice now I define this probability of being in model 0 as rho, which means the probability of being on model 1 is 1 minus rho. So the posterior basically of model 0, it is written in this nice expression using Bayes' rule. Okay? So this is the likelihood under model 0. And remember, in model 0, the parameters are fixed. So that's why I have theta 0 times the probability of model 0. And then on the denominator, I have the normalizing factor, which is this term plus 1 minus rho times the marginal likelihood of model 1. Okay? So you can actually, with this type of calculations, you can compute posteriors of models even if the parameters are living in completely different spaces, right? One model can have only one parameter, another model can have 1,000 parameters. So what I wanted to tell you so we can finish, we have only 2 minutes, okay? Somewhere there was one slide that, nope. Right, so if you have two models like what I just presented, right, model 0 and model 1, okay, you need to be sure if you're going to use this type of calculations and Bayes factors that these priors are properly normalized. If those priors, they're not normalized, like, you say uniform things from 0 to infinity, then the Bayes factors that you get can give you completely misleading results. So, when you try to compare models, when you use unnormalized priors, which means uninformative priors, you work with Bayes factors at your own risk. Okay, at your own risk, literally. So I have some examples where they demonstrate that if these two distributions are normalized, you actually can get anything you want. And even there is another extreme. If you actually take this to be normalized, for example, you can take this to be a Gaussian, and then you say, because I am not sure about the variance of that Gaussian, how about if I make the variance to go to infinity? Well, still the results come to be garbage. Okay, so bottom line, never use Bayes factors when these distributions are uninformative, unnormalized, or the limit of proper distributions. The limit is the case, with the Gaussian taking the variance to go to infinity. So basically, the examples I have are trivial, but I give you, let's say, calculation of Bayes factors, where I show you if the variance, let's say, in the prior varies, you can actually get any answer you want to. You can make any model to be the best. Okay? So this type of calculations are extremely misleading, and this is a very similar popular example that goes under what is called this Jeffreys-Lindley paradox. We don't really need to care about this type of things in this class, because we're not going to do these mistakes. So what I want you to know from the lecture today is how to compute the marginal likelihood, the Laplace approximation, and this Bayesian information criterion. Those are essential tools that basically you would need to use if you do inference in the Bayesian setting in your own research. All right, so tomorrow I'm going to go back to give you the summary of the regression problem, and then I'm going to finish by applying that regression problem to the case where the noise is also known. Because if you do experiments, you have no idea of the data, what noise they have. So you really need to assume something prior about that noise and then integrate the noise out. Okay, so we'll do this tomorrow. By the way, read the slides for tomorrow, because there will be too many things and I want to finish them up. Most of them are already things you already have seen.